It is easy to apply loads to a finite element model, and even easier to do it the wrong way. The reason why this is deceptively difficult is the same reason why it's hard to draw a free body diagram in statics. You need to consider a part or a system and figure out all the ways that it's connected to the universe around it so that you can cut it loose and put it down on the page or put it into the computer to make a finite element model. There are lots of ways to apply loads in finite element analysis. In this video, I'm not just going to show you how to push the buttons in Apex or explain what's going on under the hood. I'm going to take you through the process of designing a finite element model. We will focus on a few simple case studies that have idealized stress states. But the principles that we'll discuss will generalize to complex real-life problems. Let me give you some specifics of what we're working on. We're going to focus on applying a load to a block in tension. We're going to try applying the load to the block in a very simple way, and we'll find that that leads to some problems. Then we'll try scaling the force. That'll fix the first problem that we have. That's still not going to resolve things, so then we'll have to look at the Nastran documentation and ultimately try solving this problem a lot of different ways and see what works out and why. We're also going to model a rod in torsion 2 different ways, in bending in 3 different ways. We're going to bring this all together in the end with some conclusions, but I'll introduce those conclusions as soon as they're relevant. The goal of this uniaxial tension scenario is to create uniform uniaxial tension within this block. We would also expect the deformations of the block to be likewise uniform. The block is rigidly affixed to a support at the bottom, and a force is applied to the top. We want that force to be applied uniformly. That should lead to an ideal uniform stress state throughout this block. Let's keep things simple. We'll use a block that's 1 cubic meter. It'll be steel. We'll apply a load of 1 Newton with the dimensions that we have. That should give us a stress of 1 Pascal. How do we do that? Let's go see this in Apex. Okay, I'm in Apex. I'm going to Geometry Primitives, Box, and I'll enter dimensions of 1 by 1 by 1, and set the origin as 0, 0, 0, the origin. And I'll click the green check mark to apply. I'm going to use a relatively coarse mesh. I'll click Solid Mesh. 0.2 meters will give us 5 by 5 by 5 elements. I'm selecting hex elements. Linear elements are going to be perfectly fine for demonstration purposes. Higher order might be better for real-life applications. So the block is now meshed. Now let's apply a load. So I'll click on Loads, Force, and I just want to apply a load of 1 Newton. For scale factor, I enter 1, and for Fy, I also enter 1. Let me rotate the block so now the Y direction is pointing up, and I'll click on the top of the block. And I'll close that. Now I'm going to constrain the bottom of the block. I'm going to click Constraint, and I like to make separate constraints for X, Y, and Z for demos like this. So its name is X, I'll click Translation in X, and I'll use the Edge Pick Filter to select the part of the block that's on the Z-axis. Now I'll change the name to Y, so I'm constraining in the Y direction, and I'll click the Face Pick Filter to pick the entire bottom surface of the block. Now we'll do Z. Let's pick the translation in Z, and we'll pick this edge. I am applying constraints this way because it's very important that we resist that applied Y direction load. The X and Z constraints are suitable to keep the block from sliding a little bit accidentally. Now let's apply material properties. One way to do that is to just open up any education custom tool, and that will at least load up the material properties. So if you click on materials now, you see that there are some properties that were loaded by us simply opening an education custom tool. Now I'll click 3D element properties, create 3D element property, and type steel 3D. And I'll select a material ID of steel. Now I click Assign 3D Element Property, and I'll click on the part. Let's get this simulation ready to run. I'll right-click on the part and click Place in Analysis Scene. And let's hit Run and see what happens. Now let's go to post-processing. Let's see what the results look like. I'll rotate the block so that Y is pointing up, that y surface, and I'll do a fringe plot. Oh, this is a disaster. So the stresses look pretty non-uniform around the block. They're really high at these corners. And also the magnitudes are really bad. I was expecting a uniform stress of 1 Pascal, and instead I see a minimum of 35 going up to 150. What is going on? I can get some sense of what's happening by looking at the applied loads. So let's make a vector plot of that. So I go to the vector plot panel here, and I'll select quantity applied load force. To have an easier time seeing all of the force vectors, I'm going to turn my model shown here to wireframe. And I see that I've got my force vectors, they are all 1 Newton. Oh, that's the problem. I wanted to apply a load of 1 Newton total to the top of the block, and instead I have a force of 1 Newton applied to every node at the top of the block. Because we have 5 by 5 elements, we have 6 by 6 nodes, so 36 nodes, leading to a total force of 36 newtons, an average stress of 36 Pascal, and that's about what we see at the bottom end of the part here. Well, what if I went back to the model view in Apex and just tried to scale force down by a factor of 36? Then I would be applying a total load to the top of the block of 1 Newton, which is what I wanted. Let's try that now. So I'll click Model, Loads, and double-click Force. And I'll change this force to 1/36, which is 0.02777. And click the green check mark to apply, and click the yellow runner to rerun the simulation. I'm going to view the finite element model as solid. It looks like the stresses are a lot better. The minimum stress in the part is about 1 Pascal, 0.975. Still, we have these stress peaks at the corners, so rescaling the force helped some, but it didn't get us all the way there. To give another perspective on what's going on, let's look at the reaction forces. I'm going to make the finite element model be shown as wireframe so that we have an easier time seeing those constraint reaction force vectors. And I'm going to use the probe tool so that we see some specific numbers. I'll select a probe target of vector, and I'll click on these nodes here. Let me change the units from newtons to millinewtons so that I have an easier time seeing the exact force values. What we see here is that the force vectors are highest near the center of the part, all along those central nodes. For nodes that are at the edge of the part, the force is a little lower, and the force is very small at the corners of the part. And I'll tell you now that the reason why this is that this node here only has to support 1 element. This one has to hold down 2 elements, and this node here has to hold down 4 elements. And if we look at their reaction forces, they are about 10, 20, and 40 millinewtons, so directly in proportion to the number of elements that they're holding down. The stresses in the elements are uniform, but the elements are being held down by forces only at the corners, and so the more elements that you have at a corner, the more reaction force you need there. Now the stresses looked pretty uniform at the bottom of the block, and for us to get that, we needed non-uniform reaction forces. So maybe we need forces to be applied at the top in some other way other than perfectly equally. And that actually having equal forces all across the top gives us unequal stresses. Well, surely somebody's had this problem before. That tells me that it's time to go look at the documentation and see, are there other options? Are there best practices that we could use? That brings me to my first tip. If you're having trouble making a modeling choice in MSC Apex, you should use the MSC Nastran documentation. Nastran is the solver that powers Apex. I'm going to show you how to navigate the documentation and give a couple of examples of the types of insights that it can provide. When you install the Nastran documentation, you get a one-page PDF that links to the entire library of Nastran manuals. If you're getting started, the most relevant ones to read are the Getting Started Guide and the Linear Static Analysis User's Guide. The Quick Reference Guide is also very helpful if you want more detail on specific points. Let's take a look at the Getting Started Guide, which has some information on how to apply loads. If I go to Applying Static Loads, we get this really nice overview showing different types of loads. It refers to a force as a concentrated load, which is a clue that the force is getting applied to discrete points on the part rather than across faces. I also see that there are things called p-loads and variations of p-loads that apply forces to element surfaces and maybe to surfaces of objects even. The Nastran documentation gave us the idea of, instead of just applying force, using pressure to apply a load. If we were to have kept reading, we would have found out about a couple of other ways to distribute loads. I'll just tell you about them now. There are these things called R-type elements, so that instead of applying a load directly to your model, you apply the load to the R-type element, and then the R-type element would distribute the load across the part that you're modeling. The two big types of R-type elements are called rigid or interpolant R-type elements, or in Nastran RBE2 or RBE3, or in Apex a rigid discrete tie or a compliant discrete tie. A rigid discrete tie lets you pick a few attachment points, and then they would all be stuck to what we would call a reference node, and that is where you would apply the force. These attached points are rigidly affixed to this reference node, but that means that they're also now rigidly attached to each other. Therefore, rigid R-type elements add stiffness to a model, which might be undesirable, or you might need to work around it in some way. Interpolant R-type elements they might seem a little simpler and a little nicer. You create a new reference node, and that reference node has a very soft connection to a few attachment nodes on your part. This does not add stiffness to the model. If the attachment nodes move, the reference node moves in a way that is the average of those, and that's why we call it an interpolant element. It's because its motion is averaged from the attachment nodes. One of the challenges in using these interpolant R-type elements is how the force gets applied from this reference node back onto the attachment nodes. I'll explain more about that later in context. My next tip is, if you're choosing between modeling techniques, you're not sure which is the best one to use, make test models to compare them. The test models should be simple so that they run quickly and are easy to interpret. Here's my plan for my test models that I'm going to build in Apex. We started with just applying a force to the top of the cube. Well, let's make 5 copies of that cube and try things a few different ways. We'll use the pressure loads, RBE2s, RBE3s, and we'll do the 2s in a couple of different ways for reasons I'll describe later. The last approach will be to create a new part and glue it to the old part. We will apply the loads to the new part and hope that the stresses get smooth before they reach the part that we're interested in. So let's put that plan into action. We're back in Apex. I'm going to pull up the transform tool and use that to make copies of this cube. So I've selected the copy option here, and I can click on the cube, click on this axis here, and I can enter how far I want the copy to be placed. The cube is 1 cubic meter, so if we type in 2 meters, that will give us a new cube that is a generous distance away from this one. See? So that looks like a pretty nice spacing. I can come in here and type 4, 6, 8, and 10. Remember how we have this final cube and we'll want to put a block on top of that, so let's close the transform tool and reopen it. Again, I make sure that I've got copy selected. I'll click on this block, click on this axis now to bring it up, and this time by just 1 meter, so that these blocks are barely touching. Now let's apply loads. I'll click on loads and constraints, and this time I'm going to use pressure to create a pressure load on one of the blocks. I'm going to select total load as the type, and I'll set the Fy as being 1 Newton, and I click the top face of this cube. Now let's apply forces using RBEs. I'll click on this force tool, and remember that earlier we did direct application of force. Now we're going to use remote. I'll click rigid to create an RBE2 on this face, and I click the point in the middle to say here's where the force is actually going to be applied. And for the next block, I will also click on the top face and then click that central point. For this block, let's make an RBE3, a compliant discrete tie. I click on that top face and the point in the middle. Finally, let's apply a force to this top block in the same way that we had done before, using direct application. Remember that the magnitude now needs to be 1/36 of a newton for it to be scaled properly. So 0.0277. I've applied that force. Next, we need to connect this block to this block. We do that using glue. We'll go into Interactions and select Interactions, Interaction, and then Glue. I simply have to click the two bodies that I want to connect, and now they're glued together. I can inspect that connection here in the model browser. Now I'm going to expand the constraints that I had already so that they apply equally to all of the blocks. So I'll select Constraints and X in the model browser. Remember that this was applied along the z-axis of this block. I will pick the analogous edge of each of the other blocks. And now I can hit the green check mark to apply. And I'll hit Close. Next I'll click on Y. Select the bottom surfaces of all of these blocks using the Faces tool in the Pick filter. And click the green check mark to apply. I'll double click Z. Remember that that was along the X-axis, and I'll use the Edge filter to be able to pick the analogous edge on all of the other blocks. And I'll click the green check mark to apply. We are almost done getting everything updated, going from just having one block to a total of 6 blocks. The geometry got copied, and with that came the mesh and the material properties, which is very convenient. One more thing we need to do is to tell Apex to actually apply all of these new loads that we've created. We'll go to the Studies tab, double-click on Loads and Constraints, and we can click this check mark here to select all the forces. If you're using the new scenarios in Apex, the process is a little bit more complicated. You would have to create a load combination. Now let's close this. Do we have anything else to do before we run? Oh, we see this reminder here that we should do an analysis readiness check. Let's go to the Analysis Readiness tab. This shows us that we're missing the coefficient of thermal expansion for the discrete ties. Having a coefficient of thermal expansion doesn't seem important to this problem because we don't have any thermal variation, but it could be important for problems where that would be considered. It's best to make sure that you're running a model without any warnings present, so to disable this, we'll simply set the coefficient of thermal expansion to 0. I can double-click on this item, and this gives me the details of what to do. So I'll double-click on this node tie here, and click on this here, and enter 0 for thermal expansion coefficient. And I'll repeat that for the other node ties. Let's see how each of these loading options did. For the pressure load, the stress distribution wound up being ideal. For the RBE2, we have a little bit of a problem, but we did a trick with the RBE2 that made it work out great. The RBE3 gave us the same problems that we had originally. And using the force being applied to a separate block that's connected with glue gives us a stress distribution in the part that we're really analyzing that looks very nice, and the deformation's totally reasonable. Let's go into these in a little bit more detail. The simplest way to apply force to a part made of solid elements is to use a pressure, a P load 4, to apply force. The RBE2 gave us a little bit of a problem. The RBE2 was perfectly rigid, and so the sides of it weren't allowed to contract. But remember that as we pull up on this part, it should also narrow because of the Poisson effect. To get around that, I did a trick with the RBE2. Typically, RBEs are connected to all of the degrees of freedom of an element. So for a solid element, that's X, Y, and Z. However, we only have to select some of those degrees of freedom. In this case, we can choose only the Y degree of freedom because that's all that we need to apply the force. I was able to select only the Y degrees of freedom, so the X and Z motion of the nodes was allowed to be what it needed to so that the block could narrow. Let me show you now how I did that earlier. I skipped over that step. So I clicked on Model, double-clicked on Discrete Ties, selected Discrete Tie 1, and this second discrete tie I can click on the pencil here to modify it. And under Distribution Properties, I clicked Customize, and then I selected only the Y translation. So this way, the RBE is only able to apply vertical forces to those nodes, and they're otherwise free to move. I'll click the green check mark to apply. And I'll click this green check mark to apply also. Both of those are necessary. The RBE3 solution was ultimately unsuccessful because it applied the load equally across all of the nodes in exactly the same way that happened when I had made 36 different force vectors. What is convenient about the RBE3 here, at least, is that I didn't have to rescale the force. I applied the force to the RBE3, which then divided it equally among all the nodes that it was attached to. Finally, I would say that this option here with the force and glue worked out really well. Having a new part added, applying load to the top of that, and then letting the load be transmitted between the new part and the part that we're originally wanting to study. This is a great example of St. Venant's principle. St. Venant's principle simply says that the farther that you get from the point of application of a load, the less it matters exactly how it's applied. And we see that this part that we've added gives room for the stresses to go from very non-uniform to very smooth and uniform. And so we wind up with this part here, far from the point of load application. The stresses in this part here are very nice and uniform. And another conclusion to bear in mind is, when in doubt on how to apply loads, use more detail. And for more complex problems, that might mean something like you need to really model all the other parts in the system, or at least a few more. You might need to model contact. You might need more detail in how you model bolts. In this case, we're just modeling another part. Now let's talk about another scenario. The goal of this scenario is to simply model textbook torsion stresses. So the stresses should be constant with the length of the rod and linearly increasing from 0 at the center of the rod to a maximum value all along its outer edge. The rod is rigidly affixed to a support on one side. On the other side, we have applied a torsion load. Let me show you what I saw when I ran the model. I actually ran it twice, with applying the moment using a rigid RBE2 and a compliant RBE3. With the RBE2, I saw a maximum stress of 412 megapascals, which was within 1% of what I got from hand calculations. With the RBE3, the maximum stress was 500 megapascals. Not only that, but the stress distribution for the RBE3 doesn't quite look right. For the RBE2, stress increases linearly from the center to the edge of the rod, and stress is uniform along the outer surface of the rod. This is exactly what we would predict from theory. In contrast, for the RBE3, the stress is extremely high along the edge of the rod, but then falls off as you go closer toward the center of the rod. The stress is also very high right at the end of the rod, but not along its length. What's going on here? To get a little bit of a better understanding, let's talk about how RBE3s apply loads that are torsional. When you use an RBE3 to apply force, that force typically gets distributed equally to all of the attached nodes. But how does a moment get transmitted? If you look at the Nastran Linear Static Analysis User's Guide, you'll find out that the load gets transmitted in a way analogous to a bolt pattern. To make a long story short, the force is going to be higher the farther that you get from the center of mass of the nodes. So farther away nodes get more force. This is very close to what we want, where we would expect stress to increase the farther you get from the center of application of this moment. So let's see how this plays out in practice. Let's actually zoom in on sections of these rods. For the RBE2, the stress increases basically in proportion to the distance from the node to the center of the rod. So here we see an outer stress of 412, and then a stress for the next node in of 337 megapascals. In contrast, for the RBE3, the stress drops dramatically from 512 to 320 megapascals. Oh, not only that, but things are more complicated. If we look here, we see that there's a spot of very high stress, and there's actually 4 corresponding stress peaks. So if we go in along this line, we go from 525 all the way down to 367, then back up to 402 megapascals. What's going on here? Like we saw earlier, when you apply force equally to nodes, the nodes that are attached to fewer elements get more stress. So here we get comparatively more stress to the nodes that are at the edge of the rod, where the nodes are attached to only 3 elements. And if we look at the stress hotspots within the rod, those are places where the node is attached to 3, not 4 elements. So that's why we see the high stresses that we do. The RBE3 is simply not distributing loads in a way that's very useful for applying a load in torsion, at least the way that we have things set up here. Now recall that people are sometimes concerned about using RBE2s because they add stiffness to the model. In this case, that's a non-issue. The stiffness that's added to the model would prevent a change in shape of the end section of the rod. However, a rod undergoing torsional twisting doesn't actually have a shape change, it's just that the shape rotates. So in this case, the stiffness of the RBE2 is absolutely not problematic. Based on what we've seen, it's best to use rigid discrete ties to apply moments. The rigidity of the RBE2 is not a problem for this scenario, but the RBE3 does not distribute the load in a way that's very useful. So let's look at our final scenario, bending. The bending scenario is very similar to the torsion scenario. We want to generate textbook bending stress. So we should have stress be higher at the top of the cross section and equal and opposite at the bottom, 0 along the neutral axis of this rod. We're applying the load as a moment at the end of the rod. Therefore, the stresses should not vary along the length of the rod. There is no shear force. The rod is rigidly supported at the other end from where the load is applied. Like I did with torsion, here in bending, I apply the moment in a couple of different ways, using a rigid RBE2 and using a compliant RBE3. I have added a third case, where I use a rigid RBE2 but with only 1 degree of freedom constraint. The nodes at the end of this rod here are connected to the RBE with their x, y, and z degrees of freedom, and likewise with this RBE3. But for the RBE2, I only am transmitting load with the x degree of freedom, and the nodes are free to move in the y and z directions. So let's look at the results. First, we've applied a moment with an RBE2 with all degrees of freedom being activated. The stress profile here looks reasonable, but it's not perfect. In this case here, where we have an RBE2 but with only 1 degree of freedom activated, the one that we need to transmit the moment to the nodes, the stress profile is perfect, and the magnitude agrees very well with hand calculations. Look again, the stress contours are horizontal, stress is only varying with the y-coordinate. So why is the RBE2 here, where all degrees of freedom activated, why is that causing us problems? It wasn't a problem with torsion. Why is it a problem with bending? Now, you might not notice it, but the cross-sectional shape of a rod in bending in real life really does change if the rod bends. The top of the rod is in tension, and so we have elongation in the x-coordinate, so we should have shrinking in the y and z coordinates. And vice versa, at the bottom of the rod we have compression in the x-coordinate, so we should have expansion in the y and z coordinates. Not by a huge amount, but the RBE2 here doesn't allow that to happen at all, and that distorts the overall stress profile. In contrast, the RBE2, with only the x degree of freedom activated, allows the top and bottom of the rod to relax in the transverse directions, and that removes these artifacts that we saw with the RBE2, where all degrees of freedom were activated. Finally, with the RBE3, we have problems that are analogous to what we saw earlier with tension and torsion, where we have very high stresses at the top and bottom edges of the rod here. And the reasons for that are the same as what we've discussed already. Now let's look at the support end. So this is the other end of the rod. The stress distributions look ideal regardless of how we actually applied the load. This is another example of St. Venant's principle, where the farther you get from the load application point, the less it matters exactly how you applied the load. Let's sum things up. One thing to remember is that we need to be able to translate between FEA terminology in general and how we see things labeled in Apex or Nastran. So we often want to apply a force to a face. In Apex, that's a pressure and specifically a total load, but in the Nastran documentation, you'll want to look up a P-load 4. In finite element analysis, we might want to apply a force to a node, and in Apex and Nastran, that's simply called force. R-type element is one of the general terms for this kind of thing. In Apex, they're called rigid or compliant discrete ties, and in Nastran, RBE2 or RBE3. I'm going to point you to some helpful resources. Links are in the description. Steph Evans recently had a post on LinkedIn about applying loads using RBE2s and RBE3s. Images for that post were taken from his course on finite element analysis with MSC Apex and MSC Nastran. I've taken the course and it's the most fun that I've had with Apex. For more on St. Venant's principle, check out this video by Tony Abbey. He has other insightful videos on his YouTube channel also, and he offers courses through NAFEMS. Finally, Practical Finite Element Analysis by Dominique Madier is my main reference on how to make modeling choices. Here are a few points that I would like you to remember. First, if you're having trouble making a decision in MSC Apex, use the MSC Nastran documentation, because Nastran is the solver that powers Apex. When choosing between modeling techniques, make test models to compare. The models should be as simple as possible. To apply loads to solid elements, typically use P-load 4 or pressure for force, and use RBE2 or rigid discrete ties for moments. When using RBEs, it helps to only set the degrees of freedom that you need so that you avoid adding unnecessary stiffness to your model. Use St. Venant's principle, the idea that the farther that you get from a boundary condition, such as a load or a constraint, the less the details of that boundary condition matter. And finally, if you're choosing between modeling options that all seem reasonable but lead to very different results, you need to add more detail to your model. I hope that's helpful for you wherever you are in your journey of learning finite element analysis. To access Hexagon simulation software for free, check out the links in the description. Leave questions in the comments or message me on LinkedIn, especially if you're interested in talking about finite element analysis. Have a great day. Bye.